I won't dance, don't ask me. I won't dance, don't ask me. I won't dance, madame, with you. My heart won't let my feet do things.
What is linear programming? Linear programming is going to seem at first to be a simple extension of graphing linear inequalities, but the practical applications to science and business are enormous. However, before we look at applications, a little history. The development of linear programming was spurred by military problems in World War II. The United States Air Force, for example, was involved with problems of airlifting supplies and personnel, deploying aircraft more effectively, and determining who's going to need what airplane parts. The results of this research included the application of mathematics to the Berlin airlift and to Air Force allocation. For example, suppose a manufacturer is producing televisions at several different cities in the United States. As orders from various locations come in, distribution must be organized so that the shipment costs are minimized. This is the typical programming problem, since the most advantageous allocation of limited resources is sought. It's easy to see that the optimization process in business is vital. That's when you find the minimum cost, the maximum profit, or the minimum use of resources. One type of optimization problem is linear programming. Linear programming is when you have a two-dimensional linear programming problem that consists of a linear objective function and a system of linear inequalities called constraints. Most of our problems are going to look like this. The objective function will give us the quantity that needs to be maximized or minimized. The constraints will determine the set of feasible solutions. Every point in the yellow region satisfies the constraints, but it can be shown that the optimal solution must occur at one of the vertices of the region. We're ready now to look at a typical linear programming problem. We need to find the maximum value of that objective function, c equals 3x plus 2y, and we have the following constraints. Now, x is greater than 0 and y is greater than 0 simply means our answer is going to be in the first quadrant. Now let's graph that third equation. X minus y is less than 1. The boundary of that would look like this. So our solution is going to be somewhere above that line. The next line we graph, the solution is going to be below that line. So taking all that into account, our region of feasible solutions is going to be in the yellow area. And the optimal solution is going to be at one of these four vertices. Our last step is to take a look at each one of those vertices in the objective function. If we plug in the first one, 0, 0, our value is, the function is 0. At 1, 0, the value of the function is 3. At 2, 1, the value of the function is 8. And at 0, 2, the value of the function is 4. So in this problem, we find that the maximum value of the objective function, c equals 3x plus 2y, can be found when x is equal to 2 and y is equal to 1. Now we're finally ready for a more practical problem. Besides aircrafts and televisions, another example might be decisions farmers need to make every year. Farmers often have a difficult time in late winter trying to determine exactly what crops to plant in the spring. There are many factors to be considered: new government regulations on maximum crop production, seed costs, labor costs, fertilizer expenses, fluctuating prices of the grain market, and the weather. Now let's consider Joe Washington, who has a choice of planting a combination of two different crops on 20 acres of land. For crop A, seed costs $120 per acre, and for crop B, seed costs $200 per acre. Government restrictions limit acreage of crop A to 15 acres, but they don't limit crop B. Crop A will take 15 hours of labor per acre at a cost of $5.60 per hour, and crop B will require 10 hours of labor per acre at $5 per hour. If the expected income from crop A is $600 per acre, and from crop B is $520 per acre, how should the 20 acres be divided between the two crops in order to maximize profit? Well, thanks to us, Mr. Washington can use a procedure called linear programming to help him maximize his profit. Many practical problems can be solved using this method. The nature of these problems is that certain constraints exist or are placed upon the variables, and some function of these variables must be maximized or minimized. The constraints are often written as a system of linear inequalities. The following procedure can be used to solve any linear programming problems. Number 1, define the variables. Number 2, write the constraints as a system of inequalities. Number 3, graph the system and find the coordinates of the vertices of the polygon that's formed. Number 4, write an expression to be maximized or minimized. Number 5, substitute values from the coordinates of the vertices into the expression. Number 6, select the greatest or least result, depending on what we need. One thing to consider when students attack a problem like this, a real-life application, is that there's too many numbers, too many variables. Well, remember, we're trying to just figure out how many acres, so try and strip away all the money numbers that you heard. That's going to be our objective function, the cost, the maximum profit. So just think about the number of acres. So we're going to set up our graph this way. Now, the first thing we have to consider is that crop A, we can't put any more than 15 acres. So our first line is going to be here. Crop A can't be greater than 15 acres. So our solution is going to be somewhere to the left of this problem, this blue line. The number of acres, crop A, has got to be less than 15. And when we add them together, the two crops together, the number of acres we use can't equal more than 20. So the solution is below that line and to the left of the blue line. And so it's in this yellow region, and the best solution is going to be at one of these vertices. So the only thing left to do is calculate the objective function. For crop A, we're going to make $600 per acre, but we've got to subtract from that the amount we spend on seeds, which is $120 per acre. Then we got to take away the labor. Now the labor was 15 hours per acre, and we're going to pay them $5.60 per hour rather. So that simplifies to $396 per acre we're going to make. For crop B, we're going to make $520 per acre, but we got to take away $200 for seeds and 10 times 5 for labor. So that's $270 times crop B acres. So the profit function, therefore, is going to turn out to be P of X and Y, 396X plus 270Y. All we need to do now is plug in those four vertices. So the profit function at 0, 0 is, understandably, 0. The profit function for 15 acres of A and none of B would be 5,940. The profit function at 15 acres of crop A and 5 acres of crop B would be 270 times 5 is 7,290. And the profit function for no A and 20B would be 396 times 20, or 5,400. So from our calculations, it seems that the maximum occurs at 15.5. Thus, Mr. Washington should plant 15 acres of crop A and 5 acres of crop B to obtain the maximum profit of $7,290. And that's all there is to linear programming. Some of our problems are going to be very simple, some of them a little more complex, but you can do them all. Here endeth the lesson. Thank you for your time and attention.
I know that music leads the way to romance. So if I hold